right? We've got one more thing to chat about in 3.1. We've looked at polynomials, developed a few rules, and altogether that lets us take derivatives of full-on polynomials, even things with negative exponents or fractional exponents. Let's now talk about the exponential. What is the derivative of f of x equals e to the x? So it turns out this is a pretty short conversation, so it makes sense just to kind of tag it on to the end of this section here at the beginning. F of x equals e to the x. Let's see. Okay, so if we were to apply the definition of the derivative, that would look like the limit as h approaches 0, e raised to the x plus h minus e to the x all over h. Okay. Now you might think, wow, I've never tried to tackle a limit quite like this. Yeah, this is a tricky one. So we're going to walk through it together here on the screen. How are we even going to begin to simplify, right? And you think, I'd really like to plug in 0, but that'd be e to the x minus e to the x, right? 0 over 0. So there's some kind of work we're going to need to do. Here's the way we'll start. It's pretty clever. Notice that e to the x plus h. That can be rewritten like this. E to the x plus h is the same as e to the x times e to the h. I think back to exponential rules from algebra. If they have the same base, then you could combine those together by adding the exponents. Well, if you can combine them together to add, then you can go in the reverse as well and call this e to the x times e to the h. Why would we do that? Well, notice now both terms of the numerator have an e to the x. So that can be factored out like so. Not only can it be factored out of the numerator, leaving e to the h minus 1, but we can actually take that e to the x all the way outside, even in front of the limit. How are we allowed to do that? Why can we take it even out front of the limit? Because e to the x does not have an h involved. The limit is as h goes to 0. So if we have a factor that does not involve h, then it's not affected by the limit. And we can look at the limit of the other parts and then simply multiply that by e to the x. Okay. Now, here's where it gets interesting. What are we going to do? Okay, like so far so good, I guess, but what are we going to do with this? The limit as h goes to 0, e to the h minus 1 over h. We still can't plug 0 in. It turns out that we're going to just kind of confirm what this is graphically. So we're not going to see the full like proof of what this equals, but I think we'll be pretty convinced at what happens if we're to graph this right here and look at it as it goes closer to 0. Let's go ahead and do that together. Okay, so we're going to look at y equals, and we're going to use x's just for the sake of this program. But there it is, right? E to the h minus 1 over h using x's. What happens as we approach 0? Well, there it is. Let's zoom in. There's going to be a hole there. But what does that seem to be approaching? Right, there's the hole right there at 0, but it's pretty clear that's passing through 1. And yes, that is correct. Even graphs are not, things like this. You want to be careful. Like maybe it's actually really close to 1, but not 1 itself. In this case, it is 1, so we can confirm. Okay. Going back to the lecture. So this limit here worked out to be, that whole thing just worked out to be 1. So this reduces to e to the x times 1. Well, e to the x times 1 is e to the x. And there we have it. Now, this is fascinating, and everybody should be like just blown out of their seats, knocked your socks off, you know, whatever. Look at that. Why is this interesting? That's the same as the original function. The derivative of f of x equals e to the x, f prime equals e to the x. Look, it's the same thing that it started with. Wow. Okay, so it turns out this isn't like as big a coincidence as it appears, you know, the way we have discovered this. It turns out that e to the x really was not an interesting function. Like the number e was not an interesting number to anyone until calculus was developed. When calculus was being developed, people wondered really quickly, hey, is there a function whose derivative is equal to itself? And it turned out that that was e to the x. So the reason why e to the x is so important is because of this very property. Now, it's kind of funny, like we learn about e to the x, you know, way back, you know, in intermediate algebra. So like, especially like exponential growth, population growth and that sort of thing. We use e a lot. But it turns out that nobody described any kind of population growth before with e before calculus, and that's all connected. Now you have to take a little bit more calculus, another semester or two, before you kind of start to see all of that make sense, like why that would be significant that its derivative is itself. But that is the reason why e to the x is so meaningful to us. Okay, anyway, in our case, we're just fascinated that we found a function whose derivative is itself. Super cool. Okay, so we've got this one last example. G of x equals 16 x to the 8th minus 3 e to the x. Let's find the derivative. What would it be? Well, hey, 16 x to the 8th, that's just our power rule. And then we can apply what we just learned about e to the x for this last part. 16 x to the 8th, well, we'd multiply the 8 down, it'd become x to the 7th. What about this part? That constant multiple minus 3 would carry. And we know the derivative of the e to the x is itself. And so here's the answer, 128 x to the 7th minus 3 e to the x. All of that's the same because even the constant multiple carries. And there we go. That's the end of 3.1.